Hello, good morning everyone. Welcome to the 15th edition of the ALGA, the Algebraic Geometry and Commutative Algebra in Brazil. So we will have some opening words in the end of the program today before the cocktail. So we start. Some people are arriving throughout the day, and so we start now just with Aron's talk. And in order to introduce our first speaker, I invite Maral Mostafazadeh.
Thank you very much. Hello, everyone. Welcome. And I am honored to announce the first lecture. Our keynote speaker is Professor Aron Simis from Federal University of Pernambuco. And he's going to talk about a tale of homoloidal conjectures and its related issues. Thank you, Aron.
A idade faz a gente esquecer muita coisa, não só ligar o microfone. Bom dia a todos. Pode jogar. Eu vou escrever no quadro, mas eu queria começar com um comentário. Pode aumentar um pouco? Se precisar subir. Isso. Aí, tá bom. Eu colhi isso no Notices desse mês de fevereiro. Foi escrito por uma matemática da Columbia University. Ela é jovem, ela é assistant professor. I'm sorry, I'm talking Portuguese. I'm supposed to talk English? Okay, sorry. It's okay. So, she's very young, but supposedly very brave because she's in Columbia. And she wrote this about what are the elements of a terrible talk. Since many people are going to talk, including myself, so here are the elements of a terrible talk. First of all, if you are too technical, you shouldn't. Second, not accessible to non-experts. Should be careful there too. Does not have a clear narrative, so the definition of narrative is very complicated, so she gives an example later on in this picture. Does not respect the audience. You know what this means? Is when you write something, you say, this is trivial, this is easy, and you say this all the time. This is non-respecting the audience, you know? Just because you saw this and you know it doesn't mean that it's completely trivial or easy. And the worst of all, it goes over time. You know, you go very slowly, and then at the end, no, I have some more, I have some more, I have some more. No, that doesn't work. And I added myself one, which is don't jam the board with infinitely many symbols and things that at the end you cannot read just because you are in the back. Okay, pode ir. Now, that's her recommendation. So, an example of a narrative is, you know, start saying that you are working on a problem, you didn't succeed, so many people did, you still have some doubts, or you have some conjectures, stuff like this. So according to her, a narrative helps the audience to pay more attention. Humor. That's difficult. Some people can do it, some other people don't. But remember that you are as important as the word you'll be saying, which means that you have to be present when you talk, you know, not just show things. You have to. And finally, she says something about moving your body and tone, and you know, this is the theatrical part. Not many people adhere to this or agree with this. Okay, I hope this works for all the speakers of this meeting, including myself. Pode tirar. Okay, after many years of non-writing on the board, I'm going to try to deliver this talk by writing on the board. I try to write very big, very large, as I would like most speakers to write. So the talk is about homoloidal conjectures and related issues. Actually, homoloidal here is just to attract some people from algebraic geometry, because this is a very classical thing in algebraic geometry. But essentially, most of the things will be fairly algebraic. So let's start with the assumptions. So R is a polynomial ring over a field, K. Is it visible in the back? Raise your hands if it's not. Now, about K to start. So, in principle, as you give definitions, blah, 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 these generalities, preliminaries, K is just any field, especially if you are in algebra. But, of course, sometimes you need K to be algebraically closed. Sometimes you need even to be of characteristic 0. But in algebra, we try as much as possible to avoid this hypothesis. Of course, usually, when you say that you are assuming characteristic 0, is essentially you are assuming that characteristic does not divide some crucial exponents or some numbers that appear in yours. So instead of saying this all the times, you just assume characteristic 0, so you don't have any problems. But sometimes you don't even need this. Okay. So what is the main thing, which is homoloidal? Now, this is based on a classical thing, which is called the polar I guess, the polar of VF, where F is just anything here, and this is the variety of F. Now, usually we take F to be homogeneous. So in this talk, it will be homogeneous. And sometimes we call it a form. So this lives in the projective space associated to this. I don't want to write too many things here. So the polar of VF is a classical object in algebraic geometry, in classical algebraic geometry. Actually, you define the polar of the variety of F of some given order. Now here, I'm going just to use polars of order 1. And then in this case, it becomes very easily algebraically expressed. Maybe I don't write here. So we take the partial derivatives of F, and we take the rational map defined on projective space by these partial derivatives. So these are the coordinates of the map, so to say. So this is my notation here from Pn, and so it's usual. One says Pn dual or something. And this is called polar map of F or of V of F. I once talked about polar maps in Paris to some audience, and some people didn't like this name, polar map. They say, oh, this is not adequate. But I think everybody uses this. Okay, so what is the question? So we say definition. I should have given a name to the polar map. I didn't. The polar map is homoloidal very simply if this rational map is a birational map. Are you in the back still with me? Can you read? In other words, a Cremona map. And I know that IMPA is a place where many people like Cremona maps. Very well. So this is definitions. Now, what else we have to say? So there is the polar map. The polar map is homoloidal, and it is a Cremona map. And there is also the image of the polar map, which is the usual projective closure of the image of the map, but we can also see it algebraically. Is the variety defined, or maybe with homogeneous ring is the subring generated by the partial derivatives. Okay, so recall that this lives back in R. Of course, to be a homogeneous coordinate ring, you have to regrade this. So this is up to the degree parameterization. So algebraically, more or less, you have everything over here, no? You have this, which gives you the image of the map. And you also have this so-called singular part of the map, which is, so maybe I put as a definition, the gradient ideal of F is the ideal generated by the partial derivatives. And let me give it a name, JF. So this is generated by derivatives for all i's. Sometimes people call this Jacobian ideal. It's a little bit confusing. In this case, it's okay, but since you have a more general definition of Jacobian ideal for more general varieties and rings, and sometimes you have to include the original F, for instance, if it's not homogeneous. So it becomes a little bit confusing. What is the Jacobian ideal? But if you say gradient ideal, then that sounds like old differentials. So this is it. So you have so this gives the singular locus of VF, and this gives, so it's everything more or less algebraic, and this gives the image. Okay. Perhaps if someone is interested in the origins of this name, homoloidal, this comes from Greek. I don't know if anyone knows Greek. Homalos in Greek is sort of plain, and what else should I say? I think this is not so used anymore in general, but it keeps being used in the case of a form, and it used to be found in the books, in the classical books, as a homoloidal net. N-E-T, I'm not going to. And net just meant a bunch of forms of the same degree that defines a rational map. So homoloidal net would mean that was a Cremona map. So this is a very special case where the net are the partial derivatives. Okay, now I have to introduce this, what I call analytic spread. So, as usual, definition is very easy, but then, computing and related to other invariants is a little bit more complicated. So the definition is, so I give the notation also. The notation will be L of I. Let I be an ideal. I write R in purpose because this definition is more general. You don't need to be a polynomial ring. So sometimes it's any ring, or sometimes it is a polynomial ring. It will become clear. So let I be an ideal. Consider the following algebras. So they will be, in principle, R algebras, but sometimes they become more than this. So one is the so-called Rees algebra. Of I, and I will just say here, this is like the blow up, but we give a very precise algebraic definition. So there is algebra, so there are several ways to write it. The notation is, I guess I use this notation, and is one of this. So you can define as the direct sum of the powers of the ideal. And then you have to show a few things about this as an R algebra, but you can be more friendly and say that this is isomorphic to the subalgebra of the polynomial ring in one single variable t over R, and this is generated by I times t. Okay? So you look at this, you think of this as, anything that's in t, it's in degree 1, so this is essentially in degree 1, so this is generated as a sub R algebra in degree 1. Okay? In this isomorphism is very simple too. So gives you a very intrinsic way, and this is extrinsic, so you can play with this in several ways. So this is the Rees algebra, and once you have this, you can define the fiber. Now here's many ways of introducing the terminology, the fiber cone or fiber algebra of I is, so you take R, or maybe in my original notation, I can do a very general definition, but I want to assume now that R is a local ring. So if you started with the polynomial ring, you just take the localization and the maximal idea of the variables. So this is Noetherian local. So it has this main maximal ideal, this unique maximal ideal, and you take this quotient algebra. So this is the fiber cone. And of course, this will be isomorphic to Rm in the other notation, I, Mi, etc. So this becomes the algebra over the ring of the quotient ring, the residue ring of the local ring. So it's a usual algebra over a field. And it's generated as an algebra by this, okay? So now we can introduce the analytic spread. As I say, you can give a definition in a slightly more general situation, but this is the classic of the usual. The analytic spread of I is, so we use this notation. By definition, this is the dimension of the fiber. Maybe we give it a name here, F for fiber. Sometimes we put an R, sometimes we don't. So this is the dimension of this. And this is in the sense of crude dimension, the usual dimension in commutative algebra. Now, one sees I was tempted to say one easily sees. This is wrong. You should not say this, because it depends on verifying several things. But one sees, okay? So the analytic spread is less or equal than the minimum between the number of generators, the minimum number of generators of phi, which I denote by mu of phi, and the dimension of the ring. Okay? This is, so to say, the easier part. So this is a sort of upper bound. So it comes from some external comparison of several invariants. But you would like also some lower bound. And for the lower bound, you have to introduce a new object, which was the original work of two English mathematicians, Northcott and Rees, or Rees and Northcott. So this is the reduction of an ideal. So here's definition. So let's, again, the definitions can be done fairly general, but let's stick to the local case. So given an ideal and a subideal J and R, then equivalent. First, I is integral over J. Make a comment in a minute. We have J times I n minus 1 equals n for some n sufficiently large. And now you can say something with the Rees algebra to use them again. I'm going not to write this R anymore. So you take the Rees algebra of I. So this is a finite module, I mean finitely generated module over its submodule R of J. So one can check that this inclusion gives an inclusion of the respective Rees algebra as modules over R. And these are all equivalent. Now, this is not the usual integral for rings. So this is for ideals. And of course, today one uses this without thinking of the origins of this idea. The definition is essentially the same. You take any element, satisfies an equation of integral relation, except that you requires that the coefficients are in the powers of the ideal, no? In a nice way. And this definition is, I don't know how many of you know this. This was given by Prüfer maybe 100 years ago. And this is in the paper of Prüfer, where he gives for the first time the so-called determinantal trick that many people use this in the first course of algebra. So this is Prüfer definition. And so this is different from integrality for rings. Okay, so in this case, you say that J is a reduction. I didn't say that at the beginning, no? Okay. Okay, I have to move a little bit faster, but I'm not worried because of my terrible talk advice. So what is the relation between, so this is essentially the work of Rees and Orcutt. Perhaps not exactly this way. In the 50s, or maybe earlier. And of course, to manage this well, they showed that it's difficult to give a talk with the paper in your hand because you try to use your memory and at the same time look here, but they are in different places. Anyway. So this is, they showed, among other things, but perhaps this is the main one, is that if J is a reduction, well, I should define minimal, but I don't have time to go into this, but minimal in the sense that it's not, does not contain properly another reduction. Then the number of generators of J is the analytic spread of I. One has to require here that the residue ring is infinite, a minor. And once you have this, then from this you have this corollary that the height of I is less or equal than this. And of course, we had this before. And so this is also called the codimension of I. And it's defined in terms of regular sequence, maximal regular sequence, and so on. So this is the analytic spread, okay? Now, I don't have the time to go into this, but there is a notion of being analytically independent. You say that an ideal is analytically independent if the reduction satisfies some condition. And this notion of analytical independence is like a generalization or a similar idea to algebraic independence or algebraic dependence over a field. So it's a generalization of this. And this was first, I guess it was first given by Chevalier. Where? It's difficult to say exactly when Chevalier did this because he had these two distinct periods. When in the war or before the Second War, he went from France to the United States. So he remained there and wrote many important papers at that time. He was in permanent correspondence with Weil at that time. They never wrote anything together, but many things are attributed to Chevalier Weil in this way. And it's funny because in the 50s, after the war, he wanted to go back to France, and he could not get a position in France. That was funny. But anyway, I think in 1956 or something, you know, give or take, he started a seminar with Cartan, Henri Cartan. And at that time, they introduced the first ideas of schemes. I don't know how many people know this. They really worked with this for a while, but then Grothendieck came in, and then Chevalier wrote somewhere, Grothendieck advanced algebraic geometry 50 years. So Grothendieck did everything. But even the name scheme was known to Chevalier. Okay, so this is Chevalier, very important, related to analytic independence, and this appears as a very important algebraic thing. Wow, my time is going fast. So let me just mention two conjectures, which are usually given. So first I define what is a linear type. So you see you have the Riesz algebra here. This is for any ring. And then you have the symmetric algebra. So there is a canonical map from these two. And if, let's assume that the ideal is good enough, so it has at least one non-zero divisor, we say that the grade of I is positive. we say that I is, so this is definition, is of linear type. So let's call this phi. If phi is, so this is surjective by definition, this is injective. So this is, so if the canonical module is an isomorphism. So one can see also this is not so difficult, but it's not immediate. One has to choose the right way to see it, is that if I is linear type, this implies that the number of generators of phi locally at every prime is less or equal than the height of P, which is the same as locally the height of PP. So this is a very important notion. It was originally, let's say, discovered by Michael Artin and Agata. They call this property G infinity. And later on, they were studying this for some purpose. And later on, Vasconcelos and myself, we denoted this F1 because it has a totally different impact. OK, so this is an important property of this. And sometimes you have many criteria which says that this plus some homological condition implies linear type. But linear type is really hard. So, pardon me? I'm completely lost. Where? Ah, this is the symmetrical. Oh, sorry. Okay. Okay, so I have to say at least one or two conjectures. So let me see if I can do this here. Let me call this combinatorial conjecture. So combinatorial means now that, so this is hyperplane well, I don't have time to do this. I'm just saying hyperplane arrangement and leave it this. So, I mean, this is geometric, combinatorial, but it can be done fairly algebraic. So again, R is your polynomial ring. So I start from 1 now here for some reason. And you have these are one forms in R. So if you think about hyperplane as given by one form, so these are the hyperplanes. And now you take a few things here. One is f, the defining polynomial of this, which is the product of the L1, Lm. M can be anything, but of course, for the problem not to be trivial, you take usually M, at least n. So this is the defining polynomial. And then you have two things here. One is, of course, our old gradient ideal of f. But now you have another thing, which is this. Let me call this like this. So this is the ideal generated by the m-1 products of this. And now we have J, F is contained in I, more or less by definition. One has to check this. And it's possible to show a few things. Of course, we don't have any time. I want to state at least one conjecture. But one can show a few things. This ideal has many generators, but it's a nice ideal. So I is Cohen-Macaulay codimension 1. Oh, sorry, 2. And JF is the bad guy, in principle. Okay? But it turns out that they have the same minimal components, so they are very close one to the other. Sometimes this is a saturation, sometimes it's not. But anyway, here's the first conjecture. JF is a minimal reduction of Y. Why is this interesting for combinatorics? For the following reason. If you take the fiber cone or the fiber algebra of this ideal, you find this is isomorph to the so-called Orlik-Terral combinatorial algebra, sort of. And there are still many open questions, mainly combinatorial open question, but can be translated algebraically. So the importance is that, once you have this minimal reduction of this, you are saying in particular that the Riesz algebra, or even the fiber algebra of this, is a netter normalization of the fiber algebra of this. So you have many properties coming out. So this is one conjecture. So there are some special cases which were obtained by Ricardo Buriti from Pessoa, and Torraniano from the States. So we have several cases. I have to finish now. We have several cases where one can do this, but it's open in general. We did this in general for one less than the generic case. Generic combinatorial here means that every set of n of this L are algebraic independent. So one less means that any m minus 1. And of course, you want to show that this is totally free. For any subset, it will be independent. And the other conjecture, to me, this looks more difficult, is that JF is of linear type. Now, this we don't even know in the generic case, but we know some cases. True if n in dimension at least at most 3. I mean, for n equals 2 is a combinatorial calculation. For n equals 3, you have to work a little bit, but it's not that difficult. And we don't even know. The only thing we know is that JF satisfies F1, which is that sub-condition, or G infinity. So this is totally open. There are several combinatorial I was going to give at least 5, 6, 7 more conjectures along this line, but unfortunately, sorry, I don't want to overtime. I'm already over time. Thank you.